Welcome to this lecture. So this will be a series of lectures on Julia programming language. And we have several instructors present here in the classroom. So also in the meantime, if you have any technical question or something doesn't work, we'll be helping you. So please reach out to other people who are here. Or raise hand if you have technical issue or some questions. So do not hesitate to ask. All the course materials are on the course website. So assume everybody you got the links to the course website, right? It was sent before the course. So if somebody didn't get, so it's all the course materials are available. All the course materials are available via GitHub. So you can easily download them. There will be some PowerPoint presentation. At the beginning, I will be using slightly more those PowerPoint presentation, and later we'll move just to coding. So the PowerPoint will be becoming more and more background material for whatever I'm presenting in Jupyter notebooks. But since this is introduction, there will be always some short story. What is Julia? How it works and how it can be used. So before the course, you have received the information about Julia installation. So assuming you have installed it, Julia is a fully open source language. So this is very convenient to use, does not involve any payment and so on. This language is developed here in Boston at MIT by the team led by Professor Alan Edelman. This language is becoming very hugely popular for several data science applications, including academia, but as well as business, with more and more business applications. We will be working mostly with Jupyter Notebook, but also at some point I'm going to show you Visual Studio Code. So you can either work with Visual Studio Code or with Jupyter Notebook. There is an excellent also integration with GitHub Copilot. And because of some reasons, GitHub Copilot is working really perfectly well with Julia. So if you then, if you want, for example, generate documentation for your code or unit testing or whatever, maybe it's also something we're going to show. This has very nice integration. So we'll be using mostly Jupyter Notebook, but at some point, as we also have a look at Visual Studio Code. So Visual Studio Code has integration for Julia. You install this as a plugin, and this works. So assuming that you have Julia installed, the first thing we are going to have a look into is the Julia command line. So I'm using here Windows, but it doesn't matter with Ubuntu or Mac OS or whatever. So you start the Julia command line, and the first nice thing about this is this is a very modern command line interpreter that has several modes of how you can work with this. So if you are in Julia command line interpreter, of course, we can write any Julia program as we might expect, but also the interpreter has many other modes. If you press question mark, then it goes to the help mode. Okay, so you are in command line interpreter, you press question mark, you are in help mode, and then you can find documentation for some function. Okay, so you type the name of the function and you're in the help mode, and this is the mode number one, the number one way to work with this. The second mode, if you type semicolon, okay, then you can do any command line. So basically, you can execute bash command line. So for example, I have here installed far file manager, which is like a midnight commander in Linux. Okay, and then I can manipulate files on my disk and so on. Okay, so you can execute any shell command. You exit this mode pressing backspace. So the idea about command line for Julia is that you have one place to rule and all and to control everything. Another mode for the rep is when you press the bracket. When I press bracket, the rep is going into mode of package manager, and I can see the status of my installed Julia packages. Okay, so I press status and it's showing me all the packages that are present with Julia installation. There are many more comments. If I press tab, I can see the comments for the package manager. Package manager is also available as part of the language. This is unlike like Python language. I assume you are also kind of familiar with Python language where you have pip, easy install, and conda, and you never know which package manager to use. So here we have a package manager that has its own language for installing and managing packages, and it's also but it's also programmable. So any of this comment also can also be executed. So this is the Julia package manager. And there are more modes. For example, I have not this installed, but I could install integration with the R programming language, and then I could suddenly write commands in R in the reps. I'm not sure if I have this. I don't remember. Oh, I think it's loading. Okay, so then, for example, now I can use rep for other programming language. So R is a language for data science. Probably you have heard about this. And then I could write an R command like say A, assign to R a vector of values 1, 2, 3, and 5. And this is getting executed as an R command. Okay, so this is a multi-language, multi-tool command line, and you can switch between programming languages and places, which is very nice when you are a data scientist and you need to be able to do one thing, many things in a single command line. I will be talking further about integration with other programming languages, because the nice thing with Julia is you can easily call from Julia codes from other programming languages. Especially you can natively call Fortran, C, Python, which are probably those languages have all the most useful libraries. Okay, we have the package manager. As part of the materials for the classroom, you got the information how to install all the packages. Okay, so I assume you did it. So you know you can write a script, or you can execute commands. So when I'm in package manager, so when I press the square bracket to get to package manager, then I can execute and I can execute add command and manage the packages. Now, one more thing. Before I continue, so you have the materials for the course. So what I did before the class, I did git clone and of course the materials. Okay, so I assume nothing to explain. So I've cloned all these materials. So I have here them in a folder. So I downloaded this all on GitHub. So I cloned this. And when I go to the folder, you will see in this folder two files. One is named manifest Tom, and the other is named project Tom. Those files define as virtual environment. Okay, like in other programming languages, you have virtual environment when you are managing all packages. And now, when we start programming in some folder, if you open this folder there in say Visual Studio Code, so let me try to start. Oh, I have some other projects I'm working on. Files open. Okay, but if I open this folder, where do I have? This is the folder when I put it into. If it's on Linux or Mac, it doesn't change. There's just you have a different path. Everything is the same. Okay, so yes, I trust the authors. These are my colleagues sitting in the classroom. So okay, and I load it. Then what it's doing, it's loading this virtual environment. So those two files, manifest and project Tom, are defining the virtual environment for a Julia installation. So what is inside the file? So this project Tom is containing the list of packages. So this is the list of packages you need for this course. and this was the part of installation instructions, to download, to clone the repository and to install those packages. So this is what you got in installation instruction. So this is defining all the packages for this virtual environment. And the second part of virtual environment is when you have a specific Julia installation, then you need to resolve packages to specific version. So this is very, very long file that's providing a resolution of all those packages to specific versions. Okay, and then what do you do in practice when you are in this folder, like I'm here in this folder and I run Julia? Okay, I could go package manager and say activate, and dot is the current folder, and this is activating this current environment. So now, so it's activating, so it's found this file, and now when I write status, okay, it's showing me, if you see the beginning, that this is my virtual environment. So this is the status of this virtual environment, and all the packages have been installed. Okay, so please also note that the files that define virtual environment, they are very small files. The actual package repository is being held in some different place in your drive. Okay, but here is the information. So the actual package repository, the Julia package repository is being held in your home folder. So in Linux, we present it like this, and in the subfolder .julia. Okay, so this is, I'm using here the Linux path, but in Windows, this is C users and your username, and there is subfolder .julia, and there it's storing all the binaries, okay? All the binaries, or whatever it managed to compile and so on. So all information for the packages. But the virtual environment is only containing the information about names of packages and their number and version numbers. Okay, so the virtual environment itself is very, very small. It's unlike in Python, when in Python the virtual environment can be like 2 gigabytes. Okay, in Julia, whenever you start writing a small piece of code, you are defining a virtual environment for it. So you have a specific set of packages. So here for this course, we could have defined a separate virtual environment for each day, but just for simplicity, we've defined one for all the course materials throughout the day. Okay, so these are, of course, technical issues. Should you have any questions, do not hesitate to interrupt and do not hesitate to ask. Okay, so if anything is not clear or I'm talking something which, or maybe it's too easy or too difficult or whatever, please do not hesitate to comment. Okay, so we discussed management of packages. Now, we're going to work with Jupyter Notebook. So assuming I'm in this folder, so I can see this is I can see my current folder that I'm in. So assuming I'm in this folder, I will launch Jupyter Notebook because mostly we'll be working with notebooks. As for teaching, it's probably the most practical way. So to load Jupyter Notebook, there is a package which is named iJulia. So I'm loading this package, and then I'm starting Jupyter Notebook. Sorry. Depending on preference, you could write notebook, or you could write Jupyter Lab if you are more into Jupyter Lab. I will use it as notebook. So this is a similar environment, Jupyter Notebook. So I can write notebook. And then I need to select the directory. So I need to provide in which directory I want to start the Jupyter Notebook. And with this will be the current directory, because I made sure I'm in the directory when I have cloned all of the repository. Okay, is that clear, everything? Okay, so I can run this Jupyter Notebook. And here you can see, okay, we have Jupyter Notebook and we have the materials for day 1A. And this is the introductory Jupyter Notebook, your first step with Julia. And this is something we are going to start with, of course. Okay, so to execute any cell, yes? Okay, how am I opening this? So what's happening? If I write using iJulia and then notebook, it's starting Jupyter server and it's automatically sending a link to the web browser. So it's automatically opening the web browser. If 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 you are using an environment without a GUI, say remote server, it can also be very easy configured. Usually you do this by SSH tunneling and port forwarding. So of course you could be running a Jupyter notebook, a Julia Jupyter notebook server on a remote machine, so a machine on Amazon or whatever on your computing cluster, and then via SSH port forwarding works like a charm. This -L parameter. Okay, but normally it gets started automatically, just showing all these environment variables. And as you can see, it's get loaded as localhost is localhost, and the default port for Jupyter notebook is those 4888888. Okay, so this is using the default port. Okay, so this is loaded, and this is probably the first thing usually you want to execute. It's version info, and as you can see, I'm running the latest Julia version, which is 1.10. Now, the biggest difference between subsequent Julia versions recently are the package compile time. So the time to load a new package or to load the environment and so on is much shorter in Julia 1.10. And in the old times, even 1 year ago, making first plot would require like half a minute, and for the first time when it gets compiled. And now everything with regarding to that has been very nicely improved. Okay, so but if you have a older Julia version, to some reason, say 1.9 or 1.8, all the examples should work as well. Okay, so best to my knowledge, all the examples should work with slightly older Julia version, but they will just, at the first run, they will be slightly slower because older Julia versions take longer to compile. You can open Jupyter Notebook as this, or as you can see, this is Visual Studio Code. So what I could have done, I could select Open Folder and select this folder for opening. And when I load a folder, it loads the virtual environment. Okay, I can see here on the bottom that this is my virtual environment that has been defined in Project Tom and Manifest Tom files. So those two files define me virtual environment. Just by the way, Project Tom is defining a list of packages, and Manifest Tom is some resolution, some way how those packages have been resolved to specific set of versions. Okay, so of course I could be using Project Tom without Manifest Tom and say, hey, Julia, resolve me a new set of package versions, maybe update packages and so on. Okay, so I can load this in Jupyter Notebook. If I click a file like this, then you can also work with Jupyter Notebooks from within Visual Studio Code. I think it's a matter of taste, how you want to manage colors and so on, whether you're more like this. For me, for presentation issue, it's kind of better to here because it does not its screen to show all this Visual Studio Code buttons and so on. And also I should be able to make it full screen. How do I make full screen in? I should be able to make a screen with this Firefox. Yeah, and it doesn't work due to some reason. Or I will be using like this. So it's always something breaks when you present online, isn't it? So, oh, I think I have what it's doing. This is opening Jupyter Lab. I think they've changed something. Blah, blah, blah. Okay, I don't. It should be F11 or. Okay, I will be using like this because I forgot what was the. They changed something. F11, or it was Alt F11. No, I don't remember. Okay, so this first comment, it's executing version info. So this is the version of Julia. So this is easy. This is the current folder I'm located in. So there is where I've loaded my course. Okay, I have a Julia. So PKG status is executing the status of my package installation. I could write it in different ways. I will later. So this is a string macro. I will explain this syntax in greater detail later. I could also write pkg status, which is more like command line syntax. So this is my virtual environment, and these are all packages that are installed within this within this virtual environment. Okay. So we'll be soon going through all codes and so on, but let's do some overview. It will be some talking with programming for 2 or 3 minutes. So why we use Julia? So Julia is a quite new language with the version 1.0 released in 2018. So I could say, compared to other languages, it's quite modern. It's growing very quickly, especially for science and data science purposes and whatever we call data analytics or artificial intelligence and so on. The idea behind Julia is simple. Works like Python, runs like C. So we want to have language that kind of looks like Python-ish, but it doesn't run as slow as Python. So it's natively being compiled into assembly code. Okay, this is something I'm going to show you. This is something we are going to discuss. But Julia is being compiled to native assembly code. This is exactly the same way it's done in C or Fortran or other languages. But the syntax is very friendly, and you have nice command line interface for experimenting with pieces of code. Okay, so this is here. This is here important. Another thing important about Julia is that it can be compiled also for GPU. Okay, and this is even more interesting. The same piece of code can be compiled both in CPU and GPU. And in some corner cases, you even do not need to change the code. You just say, hey, this matrix is in memory. Okay, it will get compiled. The code operating on this matrix will compile for CPU. And then you say, hey, this matrix is in memory of the GPU card, of the graphical processing unit. Okay, it will compile differently. Okay, so it can observe what's depending on type. So it's depending on type of the variables. The code can be automatically compiled either for CPU or for GPU. It's very nice. We won't be doing too much with that because this beyond the short course, but this is very powerful feature of the language. The main question that is being asked, why do we need another language? And of course, there is a long list, but the idea is it's good for as well as for prototyping, as well as for writing production code. So you can quickly write something. It's easy to write. And yet this what you write can quickly be brought to production. And another great feature about this language is metaprogramming. That is inspired by Lisp syntax. And this metaprogramming makes it possible to create domain-specific language for various functions. For example, we are going to see a domain-specific language for optimization. Okay, so you have optimization models, and since this is some area of mathematics, there is a domain-specific language. There is a domain-specific language for differential equations. There is a domain-specific language, say, for manipulations of data frames, and so on. So for several areas, this metaprogramming feature makes it possible to create domain-specific languages. And the idea is to have one language to do everything. So what people could observe in the field of data science is that very often people would be writing some data analytics code in Python, but then if there is lots of number crunching, then you need to write in C. And projects in business very often end up having components written at the same time in C and Python. And okay, if you know both those programming languages, this is no deal. But if you are in a corporate environment and you need to have here C programmers, Python programmers, something programmers, then it's much more difficult to manage and maintain. So the idea about this language is you have a language to control everything. And it works pretty well as of today. So you can really do both gluing the components, you can write high performance code, you do not need to use C, and you can also write GPU code. So again, you do not need to use C or some other specific tool. So you have one language as well as for prototyping, as well as for writing high efficient code. So this is one competition, it's MATLAB. But if we talk about high performance computing, big installation, so the biggest MATLAB license cost we have heard of is $30 million for a license renewal at a data science, a supercomputing center in Singapore. So the guy, I know the guy who needed to pay this amount, and now he is one of the biggest people promoting Julia around wherever he goes, because he doesn't want anymore to pay $30 million license. Nobody likes this. Okay, and so these are some benchmarks for programming languages. I will go quickly over it. Basically, you can see that Julia code is similar to compiled languages, but this is more interesting benchmark. So on x-axis here, you have on the x-axis, you have the code length, so how much code you need to type. While on the y-axis, you have execution time, and it's a logarithmic scale. Of course, we give execution time a logarithmic scale. Wouldn't make sense otherwise. And you can see this is the inspiration behind the language. So before Julia, I would say either you had languages which are slow or require lots of typing. Okay, so the idea was to make a language that is easy, quick to type, and that also executes fast. And maybe the third goal, this is a language designed for mathematics. You will see it very soon. You can see that this is indeed the language, which is of course true, but you can really see this is the language that has been designed by mathematicians, and you will be able to feel this. Okay, so this is how this looks like. So if we look at the key features of the language, then we have performance, we have scalability, and this includes support for single instruction, multiple data. So we have high-level language, but you can go into small details of CPU design. You have support for multi-threading and including native threads, and of course green threading like in any language. You have support for distributed so you have support for distributed computing. You can write a single Julia program that is going to spawn across many machines, and this is something we are going to discuss at the last day, and strategies for parallel and distributed computing. And Julian is working here on the stalls at Julia Lab, so he has great story in that area. Okay, and there are also things which so you will see in a minute that this is a multiple dispatch language, and the way it's designed is really fantastic for mathematics. Okay, so Julia is compiled language. So if we write a function in Julia. Okay, so suppose we have a simple function. Okay, so I can define a function like this, say function blah, blah, blah. You can see that kind of, this syntax look kind of MATLAB-ish. You have this end structure taken from MATLAB instead of say curly braces as in C or Java, or indentations as Python. Okay, this is how we define the function, or you can define also one-liner just by equal, kind of like mathematics style. So if we have a function, of course, we can execute this function, but it's more interesting what's happening with the compilation process. Namely, when you write a Julia function, it goes through multi-stage. Compilation. So this is starting with tokenization. Then an abstract syntax tree of a function is being built. And this abstract syntax tree is going then through lowering when the types are being defined. Then it's being translated to intermediate code of LLVM. So LLVM stands for so this is a well-known compiler system, which is now a big hit in several open source languages. And then it gets compiled to a native code. And we have some macros to see stages of this compilation. So if I have this function, if I have this function for 2 parameters and both are 2 numbers, then I can see that if I see a compiled code, it's going to generate a structure like this. Now this is simple function, so not much is happening. But then depending on the type of parameters, a specific implementation of the function is used. So you can see I have here 2 integers. So then it knows it needs to replace this plus operation with @int. Then further, it's being translated to low-level virtual machine code. So do LLVM code. So this is something being understood by LLVM. And in the end, it's being translated into assembly code. Okay, so this is the code that CPU understands. So this is a fully compiled language. And as you can see, you can also, so sorry, this was the fully assembly code. And of course, normally we do not look assembly code unless we want to manipulate the process somehow, but you can pick it into any point. Okay, this is kind of maybe technical, but the assembly code, of course, is going to look differently for different set of parameters. Okay, so Julia is using multiple disk path. We'll be discussing this also later. So it's looking at the type of parameters, and depending on the type of the parameters, the code is getting compiled differently. Now we'll have a more exact look at Julia's type ecosystem. So here you have information about materials also for further learning. So you can find it in the slides. Now I will move away. Mostly I will move away from the slides. And I will be discussing here in Jupyter Notebook materials. Are there any questions so far? So this was kind of introduction. So, it's a compiled language, more the syntax, of course. We'll be now discussing several syntax issues. I don't know if somebody wants to ask some question. Also, guys, do not hesitate to interrupt. Okay, so if I'm talking quite a lot. I'm trying to talk maybe faster on boring parts, or I don't know, they are fascinating. But if you want to interrupt, if you want to ask something, don't hesitate to ask. Okay, so let me define a vector. The syntax for defining a vector is kind of like Pythonish. So this is what we could see in Python. So we use square brackets, and then we have defined a vector. Okay, we can see a vector is a type of vector. And also we can see a small additional piece of information here. This is a parametric type. So this is additional information of what is the type of elements in the vector. And we'll be discussing slightly more detail those parametric types later. But you can see you have a type of vector, and there's additional parametric type. So I could do indeed something like type of V, and I didn't run the line up there. I could do something like type of V, Control Enter runs this, and you can see that this is type of vector. By the way, the type system in Julia is also using aliases, because internally this is a one-dimensional array. Okay, but this is a technical thing. So we call in Julia we call one-dimensional array a vector. Okay, and there is an alias name, so it's easier for us to look that this is a vector. But like in C or other languages, we have just array type that if it's one-dimensional array, there is alias that is named vector. If it's two-dimensional array, then it's alias that is called matrix. And for more dimensions, we just say array. Okay, but this is of course more convenient to think this in mathematic terms. Now, we can use comprehension similar to Python. So we can use mechanisms to generate elements of vectors. So I could write elements 3x, and like in mathematics, in Julia, you do not need to write multiplication symbol if it's obvious what you are wanting to do. Okay, it's sometimes basically if you have variable and some scalar and some fixed number, then you can write like 3x, like here. Okay, and it's generating a set of values. So this is easy. For x in, so this is again a Pythonish style. Now this is, and from 1 to 9, this is how we are defining the ranges. And in Julia, the last element of the range is included in the range. So Julia is using one-based numbering. This will be in a minute. And in one-based numbering language, so I mean one-based, the first element of a matrix vector of whatever has index 1. In one-based numbering, in the programming languages, that when we use one-based numbering, then all elements of the range are always included. So this includes Julia as well. Okay, so this is an equivalent. So this 1 to 9 is an equivalent of Python range from 1 to 10. You know, I assume everybody knows Python, right? So you know that the last element of the range in Python is not included, and in Julia it is. Okay, so then we got it. Then if you have a vector like this is something I mentioned. You can select the elements of vectors by providing ranges. And the first element of any vector has number 1. So this is something, so if you are coming, say, from C++ or from Java or .NET or Python or several other programming languages, here we use numbering like in mathematics. Okay, and languages which use one-based numbering is Julia, but it's also, for example, MATLAB or R. Okay, so there is a big competition. Julia is very flexible. And because there's, of course, as you can assume, in Julia forums and other forums, there was lots of discussion why to use one-based numbering instead of zero-based numbering. And as Professor Alan Edelman pointed out, Julia is so flexible, and this is true. You could use even 0.5 numbering if you wanted. It's possible to program in Julia. So if somebody wants a compromise, and of course you can configure Julia to use zero-based numbering too, but normally you don't want to. Okay. So everything will be as close as mathematics as possible. So, for example, you could do such piece of code. Square root of x1 for x1 in 1 to 9. Okay, and this is also a valid Julia code. So what do we have here? So we have the square roots time. Okay, so the first question: how do we write something like this? So to type this, basically, when you start typing in Julia, it is supporting LaTeX symbols, LaTeX symbols. Okay, so you could do something SQRT and then press tab, and it's replacing this with an appropriate Unicode character. And now, normally you would write like this in, okay, but you could use LaTeX symbol in and press tab, okay, and it's replacing, and this will work as well. So in several contexts, Julia understands mathematical symbols. How do I do lower index? Again, like in LaTeX, you press underscore, which is for lower index, and then say 1, and then press tab, and this is being replaced by an appropriate Unicode character. So you can use LaTeX type of typing of various symbols, and then they will appear. So you start then typing with slash, and then you type whatever you need, you press tab, and then a LaTeX character appears, and several of them work in very nice ways. So in Julia, when you write Julia code, you are encouraged to make your code to look as much as possible to mathematical equations. It's very good when you do a paper or when you do research, because you can keep your code almost identical to whatever you have in your mathematics code. Okay, this is something you can very quickly, very strongly love. So that's one of areas where Julia is very nice. That there are many ways to make your code look very similar to equations that you are seeing in the paper. And of course, it means easier debugging. You can easier find what's wrong with the code and so on. Julia also has several methods that you can take a piece of Julia code and generate LaTeX from it, or take a Julia object like a table or what array, a data frame, and generate LaTeX code from it. So also, if you do want to do scientific writing, in Julia you have all integrations you need. So this is really convenient. Really convenient for people doing data science, math, and also doing the stuff related to writing papers. Okay, so we have a vector. This type, we have a vector where elements are of type float. I can check also type of element of this vector. So element type, and this is float. Now, how do I define an empty vector? So if I want to define an empty vector, normally I say I use int, and this stands for empty vector. So again, it's very Pythonish. So assuming you know Python, this feels similar, but you are providing type. And in several places, you will observe that Julia would be very Pythonish, Python-like, or maybe MATLAB-ish, like MATLAB-like, but you will want to provide type. Why providing type is so important? Because when you provide type, this data can be more efficiently stored in memory, because you exactly know how big each item is and how many bits or bytes in memory you need to store each item, okay, of this data structure. You can of course do something like this, but this is not nice, because then the type of this vector are any. So it means it will be essentially a vector of pointers to some values. Okay, because you do not know how big any is. Like with integer, you always know integer is so int is integer with the of the size of the operating system. So on 64-bit operating system, so int is the size of a pointer. So when you use 64-bit operating system, int will be 64-bit. And then I know this is 8 bytes. Okay, so I know this is 8 bytes, and I can nicely store it in memory because I exactly know how big the each element of vector is. Here, this will be a vector of pointers. Very bad, many times slower, because it translates more memory usage and slower execution speed. Yes? Yes, the array is a variable size, and you can, as you can see, you can add element dynamically. Okay, this is very. You ask internally how it's being resized. I think that it's slightly more aggressively resizing. You know, Julian, if you add element to arrays, it's storing slightly more space, like slightly more aggressively resizing. I think usually you resize more aggressively because it's good for speed. Then you need to reallocate, but okay, so then you need to allocate. But following your question, there's a Julia package which is named static arrays.gl. Okay, and this package makes it sure that you have a static size of a vector. Okay, and what it results? It results that your code can be completely differently compiled because you exactly know where is everything in the memory, how big it is, and then your vectors will be kind of behaving like scalars. And here are some examples. So the speed up could be like 6 times, but of course the compilation time will be expanding, because then you need to compile a specific set of routines for each possible size of the vector. Okay, but normally we have vectors of variable size, and as it has been mentioned, and there is some underlying buffer underneath. Okay, so we now see more types, but small discussion about data types. So we usually are interested in numbers, at least when do mathematics, data science, and whatever we are going to discuss in this course. So for numbers in Julia, we have basically type hierarchy, where those types on the top, these are abstract. So number, real, and integer are abstract types. And then you have concrete types. And we have a concrete type such as Boolean or a big integer. Big integer is, it's a variable size of bytes. So it's a number with a variable size of bytes. This is what you could expect. And then you have whole numbers like 8 bits, 16 bits, 128 bits, and so on. So this is expected. The most popular type is, of course, integer of 64 bits and float of 64 bits. Now, in some cases, you might have composite types like complex numbers, but you could even define your own. So you might have idea from some different number space. Maybe it's defined over I and something else, like, multi-dimensional space, number space. You can also do this in Julia. Okay, but what is standard, we have also rational numbers, complex numbers, irrational numbers. We'll slightly look at them, as numbers are interesting for us in this building. Okay, so complex. So I could define a complex, say 1 and 4. So 1 is the real part and 4 is imaginary part. And then accidentally, what I did, I defined here a complex numbers, which is defined over the space of integer numbers. So I'm using integers to represent real and imaginary part. Okay, and when I have any object in Julia, I can dump that object to see what is inside. So sometimes we want to see what is inside a given object. So if I dump that C object, I can see this is a complex number of type int defined over those two values. Not kind of surprising, but this is how it's being held internally. So you could build your own data structure similarly, and if you have the idea for different number space, you could do it. If I want to have complex number defined over the space of floating point numbers, I can also do this. So this is here I'm defining a complex value defined over the complex number defined over the set of floating numbers. Okay, I could also define. So, for example, guess we do GPU computing. Okay, I want to do GPU computing. I could define complex numbers over the space of 32 bits float numbers. Now we can have also rational numbers. So I can define rational numbers are obviously defined over the space of integer numbers. But for example, I could define, so I could now do type composition. So I could say I want to have a complex numbers where real and imaginary part are represented as rational numbers, where parts of the rational number, both parts of rational numbers are represented as 128-bit integers. So you can compose types in Julia in any way. Actually, the Julia type system is so complicated. I think, if I remember, is Turing complete. It would be possible to write a program in Julia using only type system. This is funny. So this is very strong typing. But now this is even more surprising. If I define number like this, then suddenly everything works. So all the algebra, so there is, and so all operations defined over for complex numbers, they will work with this Frankenstein. Okay, so you can have any idea, and you can build one numeric types over the other numeric types, and abstraction is in Julia and define in such a great way that it's going to work. So you could immediately start working with such complex numbers if you need to, because you say you need this type of precision for your computations. You know, it depends on the computational problem, how you are going to treat precision, how big precision you want. In Julia, you can do it. Okay, this was a long story about numbers, but this is very powerful, and it's showing how composite type work. Okay, so to move between the types, you have parse function, which is quite obvious. Now here we have plenty example of parsing types. So this is a list of examples. You look at it, it's obvious. So there is nothing to discuss over it. Just you need to know, you can convert from whatever type you want. Now, any type is of type any. So the top type, like for example, in Java, you had the type object, and it was a top for all of the types. And in Julia, the top type is any. So everything is of type any. So this is saying is int subtype. So this is operation subtype. This operator means subtype of any, and this is it. You can have also union of types. So sometimes you do not know whether something is going to be int or float. So you could say that whether int is a subtype of union int and float. Okay, int is a subtype of union and float. We have also special type nothing, and we could say this is kind of equivalent of null. Okay, depending on the programming language, this is a kind of equivalent of null. So we have a special value nothing, and the special value of nothing is type of nothing, and there can only one nothing can exist. Okay, now text interpolation. So when you do like println in Julia, you can interpolate text like you can do in Perl or Bash. I really love interpolation in some programming languages where it exists. So in string, you can interpolate string. So $sign is for interpolating, and you can see what it's doing. A function that does not return a value, like this one, is returning nothing. So if I type res equals f from 1, and this is just printing, then it does not return anything, it returns nothing. And the type of nothing is nothing with the capital letter. Now, we have even more types. Like we could have, for example, number pi, okay? And the type of number pi is an irrational number with parametric type pi. So this is also a space for irrational numbers. And then what you can do, you can set the precision with the number of bits. So if I have 100 bits, I can show pi like this. And if I'm going to say I want pi with 10,000 bits, I'm going to see it like this. So big float is converting irrational number to big floating point number. And of course, how do I type pi? You type pi / pi and tab, like LaTeX. So each time you use LaTeX syntax. Okay. Now, there are lots of data types, and they are similar to other programming languages, so probably not to, it will very soon get, I would say, more difficult or more complicated. So some things will be fast. Any questions so far? Is everything clear? Okay, so tuples. Okay, so tuples are kind of immutable vectors. So if you have a vector and you know it wants to, you want it to be immutable, then you use a tuple. Tuple are stored in different parts of memory, so the access to tuples will be faster than access to vectors because compiler can make use of information that they are not mutable. Okay, so you define tuple in this way. Then if you have tuple are basically can do the same operations as with vectors, with exception that you cannot assign a value. This is obvious. And now tuples have a strict type of everything. So if I create a tuple like this and check what is the tuple of those two numbers 3 and 3.0, I can see it's a tuple where the first element is of type int and the second element is type float. So everything in Julia is going to have type, and it's really important to have a type in Julia for everything in order not to get lost. So another type of tuple. So now we have a tuple of 3 elements. The first is int. The second is string. And the last one is a rational number defined over the space of a 64-bit number of integers. So you can see that these types can be composite in many ways. And indeed, sometimes in Julia, we could end up having type information spreading over 3 lines. Okay, so sometimes these types can be really, really complex because there are many ways how you can join types. But the nice thing is it's building very nice abstractions for mathematics. So for an example, there is a type of abstract graph. And then if you have your own mathematical idea for graph, say, for example, you want to extend graphs, so you have libraries for graphs, and you want to extend that for hypergraphs. Hypergraph is a concept where one edge is connecting more than pair of vertices. Then it works. Okay, so you have some abstractions. If you stick to those abstractions, then suddenly everything works like magic. It's those composite types are fantastic for mathematics. Okay, matrices. So we define a matrix or multidimensional array. You can define a multidimensional array like here. You could write array, the type of elements in the array. So again, you have parametric type. Everywhere we have parametric types in Julia. You could say that you want a kind of null pointer value for these elements, and then you are providing dimensions, say 2, 3, and 4. So I got a 2 by 3 by 4 array of cars. The same you could you could do array any undef 2 and 3. Then I have 2 by 3 array. Then I have 2 by 3 array of pointers. Oh, I'm showing this here. And those pointers are kind of all empty pointers. Now, there are functions like in Python, NumPy. Zeros makes a vector or array of zeros. Ones makes a vector of ones. Truths, falses. You can create ranges and so on. So this is kind of obvious. So this is quick. So we have a special type, which is matrix, and matrix is an alias for a 2-dimensional array. So it says matrix is an alias for array with some type T, because again, everything needs to have a parametric type in Julia, so it can efficiently compile the code. And this word T, it means that this T is a parameter for type. Okay, so matrix is an alias for a 2-dimensional array. Oh, and here we're making a matrix, but we're making it funny way because we say create a matrix, do not assign any value. So undef is do not assign any value of integers size 2 by 3. And then when I execute it, it's going to allocate me some part of memory, and whatever rubbish was in that memory, it's not cleared. Okay, because it's allocating the size of memory 2 times 3 times 8 bytes. Okay, so it's like 72 bytes of memory. And whatever what was there in the memory, it was not cleaned in order to save execution time, and I'm just getting a chunk of memory. Okay, I see it's an array as a two-dimensional matrix with 2 rows and 3 columns. I can manipulate this matrix, but indeed all I'm getting is a piece of memory. Okay, so whatever rubbish. So if I execute it many times, you can see whatever what was then in memory probably left over by some other processes. I'm getting that chunk with memory. Okay, if I want it rather be filled with zeros, I could say I want an array of zeros size 4 by 5, and here I'm also assigning one value to this array, because I can mutate a matrix, of course, and then I'm getting a matrix where in the first row and third column I have the value like 66, and otherwise it's zeros. Okay, so the difference is it also takes you chunks of memory, but it fills it with 0 value. It's up to you what you need. And of course, creating a matrix and filling it with 0, it takes some time because you need to assign to each cell of memory 0 value. So maybe if the next line you are overwriting it, it does not make sense. Then we have array slicing operators. So array slicing operators will work like this, that if you have a matrix like this one, you can, from the matrix, you can select, say here I'm selecting all rows and the column number 3. So colon is in array slicing, a colon is selecting a set of rows, and then I can select any column I want. We have a reshape operator, and this is funny because Julia can work with non-materialized data. This is the example number 1 of what is non-materialized data. So suppose you have a vector of values of between 1 and 12 billion. Of course, I do not have this much memory in my laptop to hold this vector, because it's 12 billion numbers. So I would need 96 gigabytes of RAM to hold that vector. Okay, and I don't have that much. But now Julia is good at understanding that sometimes you do not need to materialize, because hey, it's exactly defined. It's numbers from 1 to 12 billion. And say I want to reshape it into matrix by 3,000 rows and 4 million columns. Can I do that? Yes, because it's not storing all of this data, it's just storing information that I have matrix of this type. And now the many algebra functions. So for example, if I want to find a minimum value over this, like minimum, okay, minimum or sum or whatever, then so minimum function is not cleverly enough implemented maybe to know immediately, so probably it's being iterated, but almost immediately I'm getting here the value. So I can manipulate this, okay? So I can work with this. I could, for example, calculate a sum of the column, the sum of the column, say 1. I think I should use maybe view a full column also, not to avoid materialization, and then I can do it. Okay, so I can take a column. So add view is also avoiding materialization, because if I write A1, I think I'm going to get some. I think it's going to be materialized into memory. So here I also want to avoid materialization. So add view says do not materialize it. And again, I'm getting this. I'm getting this. Oh, this is fast. I think I'm getting this almost immediately. Okay, so as you can see, I can have a matrix that theoretically is not fitting into my memory, but I can still work with matrix this huge. I lost the place whenever it was here. Blah, blah, blah. Oh, it got collapsed. So this is very flexible, and you can work with any size data structure. Another thing which is nice, if you can see how Julia is displaying such huge matrices, you can see it's displaying top left corner, top right corner, and those small dots to show it. It's very good because, as you know, usually if something goes wrong with your data, it's either at the beginning, at the end, or at the left or on the right. Okay, so it's nicely trying to display whatever can be seen. Of course, there are many tools then, to navigate, but this matrix is anyway too big to be shown. So this is 12 billion elements. You are not going to see till the end of your life anyway. So, okay, so now, then you can do, of course, operations over this, like say, take sub elements and so on. So this was set. So now data structures. Okay, yep. You mean what's happening here? Yeah. Okay, so no, it's not dummy. It's a correct number. So it's a correct sum of correct sum of the column 1. Okay, but what it's doing, it's most likely it will generate a loop and just generate value one by one. So there are 3,000 values in that column, but it will not generate all those values at once, but it will go iterate, like generate value one by one. And we could see, I think, if I do using benchmark, maybe just at time should be enough. Okay, so you can see it has calculated. So I've taken here a sum of a column that has 3,000 values, but this function allocated only 100 bytes. Okay, if I remove you, then you can see it allocated 23 kilobytes because it had to generate all vector. You had to do materialization of all this data. And Julia is really great. You can work very often with data structure without materializing them. Of course, you need to be careful. Okay, but now you see, and what it means in practice, it's huge performance gains. And in Julia, it's really easy to control such things as far as algebra or mathematics, is concerned. So this is easy as that. So I define those values. They are all defined, and there is 12 billion of them. But I can calculate any of those values just knowing that they are numbered from 1 to 12 billion. And Julia is clever enough to know that because it's a non-materialized data structure. Even more, I think I will not crash Julia if I try to do, or maybe I crash A+1. Okay, I should vectorize this. Maybe I try A. Let's see. I'm just wondering whether it's going to crash or not. Yeah, no. This time it's try to materialize, but maybe A times 1. Pardon? Yes, it's out. No, but it doesn't make in place. So it doesn't make sense for in place modification because it's not materialized data structure. It just depends. Some algebra operations might be supporting non-materialized data structure. We later, for example, have a look at sparse arrays, and sparse array is going to behave like array for algebra. But it's not materialized, like, you have a huge array with billions of cells, but only a small amount of them are ones. And in algebra, the functions for huge arrays have been defined, and everything is going to work. But for example, here, for this data structure, such functions were not, because this is a toy example that probably nobody is working with non-materialized arrays just having numbers one by one. So because then you need to, for some things, you need to have specific implementations. But yes, but it was still material. But I think algebra should work for ranges. Let me try to take this 12 billion elements and I multiply it by 3. Yeah, it works. So for example, algebra works for so I have a range of 12 billion elements. So I could do indeed, just show you to make it funny. So this is my range of 12 million elements. I can take this range and multiply it by 3. And then I have a matrix of 12 billion elements when each one is from each one distance by 3. Because multiplication for ranges was defined. So this mathematical operation was specifically defined not to materialize the data. Okay, because it's still 12 billion values. But I do not materialize them. Okay, and I tried to add, but addition operator for this type of non-materialized matrix was not defined. Yes, can I? You mean okay, but the point is I'm multiplying all elements. I'm multiplying all elements of the matrix. And so somebody would need to overload, and it's quite easy to do. Somebody would need to overload multiplication operator in such a way that it should know that for multiplication this thing should be used, because of course this data structure is being held somewhere inside. So this is sometimes tricky. Okay, data structures. Now, Julia is not object-oriented language. It's a language with multiple dispatch, so everything is built around the type, which is fantastic for mathematics. But sometimes we want a slightly of kind of object-oriented thinking about problems. And in Julia, you can use data structures. Also, do not hesitate to ask if you have. Should you have anybody have any questions? But you are already doing great with all the questions. So we have the data. We have the data structure. So this is sample data structure. So mutable, it means that the values can be changed, and depending on mutable or immutable, it depends how the variables are being stored in memory in either heap or stack. Okay, so here we have a data structure. Then we have fields. So suppose I have one field which is integer and the other field is float. And if I do not define the type of field, usually it's bad because it's some pointer, because it's any. So any always ends with type, with putting type in a box and having this is type boxing named, and this will be a pointer to some value stored elsewhere. Okay, and if I have object like this, I can create this object. I can access elements. I can assign value. Then field names for a given type is showing me the list of fields. And that's it. Okay, so these are type. So these are data structure. What is important here, you use dot to reference the sub-element of such data structure. Okay, so when I have defined this object, I can dump it. So dump is basically display the object, and then I can see my point that it has field x, y, and x, y, and meta. By the way, when I'm going to do something like field names of point, then you can see I'm getting X, Y, and meta. These are fields, but they are here. They have prefix with colon. Okay, and something with prefix of colon, it means it's a symbol. We'll be using those symbols on various occasions, but a symbol, for example, it could be a name of a column in a data frame. So, for example, for identifying objects, very often in Julia we use symbols. So, if I have symbol X, if I dump it, it's element of type symbol with kind of value X. Okay, so some symbol. So we will be seeing symbols at various. So sometimes, in particular, you will see symbol when you do something with symbolic computing. Okay, because then you need symbols, but they are broader. Like, for example, you could have symbol to represent a column in a data frame. Okay, so sometimes we'll be referencing those symbols. Okay, now if we have a data structure like this, sometimes we want to assign default values. Okay, and the standard syntax does not support it. Rather than that, there is a special macro that is kind of extending the syntax of the language. It's named kwdef. I think I do not need base anymore with 1.10. So there is kwdef, keyword definition. And this means that I have a data structure when I also want to define the default values. And then if I do it like this, I can create a new point. I'm getting a constructor where parameters to the constructor can contain some default value. So here I say X is 999, meta is origin, but say Y just got the default value, which is 0. Okay, so if I decorate this with kwdef macro, it's going to construct generate me a set of constructors, which I'll later use for manipulating this object. Now, this object point2, I did not put mutable in front of it. It means it's not mutable. And if I try to mutate it, so I have object p2, and say I do p2.x equals something, I cannot. Okay, it's not mutable. There is a second macro for parameters. There's a package named parameters, and it's a matter of taste which one you use. But kwdef is part of the language. But there is also a package named parameters which does the same. But the difference is that objects are being displayed in a nicer way, and there is a bigger set of constructors. So kind of it's more convenient. But this is a thing of matter of taste. So some people prefer one the other. Okay, I think there will be different examples throughout the course, but there are at least 2 ways to do it. Okay, we have then dictionaries. So dictionaries are pairs of key and values. And the only thing interesting here, you need to have type parameters for everything. You have a dictionary. Okay. Provide the type for keys and values. Okay. Everything in Julia needs to have information for type. Why? Because this compilation chain will not be efficient if it doesn't know the type. To generate efficient assembly code, you need to have the type information. Okay, so this is how we generate dictionaries. You can, of course, have dictionary of any. It's similar to dict that you have in Python. Okay, so this is easy. There are, of course, functions to manipulate dictionaries. You can add elements, delete elements, but basically you can write something like y from 2 equals it's going to assign value. So this is very similar to other programming languages, so this is not surprising. Text processing is quite standard, with exception you have interpolation. So if x is 1 to 3, I can write $x plus 3 equals, and then I put here $, it's and parentheses is doing interpolation. And suppose I want to show $sign. So $sign is a special sign in strings. So you need to do /$. Okay, so this is, no, I would put apostrophe, so the second result does not show. So this is this is what would show this part. So this is how you can interpolate strings. Now, one thing which is to remember, to concatenate strings, use multiplication. And there is a great discussion on Julia forum why not to use the plus sign, because you usually use plus to concatenate string. But you know, if you're adding numbers, you should be able to reverse orders. And in mathematics, in case of multiplication in algebra, you cannot reverse order. So for mathematic people, it was much more natural to use multiplication to concatenate string. There's a great philosophical discussion on that. So if you have time, you can read how people are thinking. That we use multiplication to concatenate, to connect strings. Multiplication of strings is then to the power of something, because it was kind of logical then. You have full support for regular expressions. So if you use a regular expression in other languages, it will be the same in Julia. Okay, and if you don't know, throughout this course, we will not be using regular expressions, so I will not discuss that in detail. But if you are programming regular expressions, say in C or in Python, it's exactly the same. Okay, then also what we have in Julia are string macros. So sometimes you want to decorate a string with a macro to change the way how the string is understood. For example, slash symbol is a special character, but in Windows, slash is being used for paths. So instead of writing slash 2 times when writing a Windows path, you can at front of the string put row. And it means it will not be using interpolation or special characters. And there are, of course, many more. So for example, if I put L, it will be LaTeX. It's for some libraries, but there are libraries that you put L in front of the string and it knows then it's LaTeX in string and it's going to process appropriately. You can, display equations. It would, depending on what graphical user used to Python notebook or Visual Studio Code, and it will be nicely displayed as mathematics and so on. So there are many, many string macros. So the easiest one is a row. Okay, so create a string without any. So the name of the macro is @row_str. So stands for macros. I will discuss macros few days later because it's not a good story for the first day of the classes. But this string macro is named row_str, and here you can just write row in front of a string. And there are many other macros. Okay, so this is about strings. Functions, we have shown functions, okay, but functions can have parameters. And this is, I think, the last thing I can do before the break. Yeah, the rest, it will be kind of like background because we go to data frame, but I will be showing the other things. So I will be discussing the other stuff already on some data examples. Okay, so there will be, after the break, there will be use case, and I will, the materials will be interwoven. Okay, so function. I have function g, and then I can have parameters. So I can say g takes parameters x and y. Okay, and these are both integers. So I can strictly define the type of parameters and say this returns a tuple of y and x. It's reversing an order of 2 parameters. Okay, I could then define a different function, g, and this time the first parameter is integer and this one is Boolean. And this type, it does multiplication. So it will return either x or 0, as you can guess. Okay, I could define another function if for other parameter types, They could be subtracted. Of course, it does not make sense here, but the point is I have many definitions of the same function with the same name, but with different parameter types. And I can show all those definitions. These are called methods. So you can have a single function and multiple methods depending on parameter types. So the first method is using an integer and Boolean. The second method is using two integer. And the third method is just for any other parameter type. Now, when you write Julia code, it's Julia compiler is navigating through all possible methods of a function, and it's selecting the one that's most appropriate. And the most appropriate is the one with most strictly defined types. Sometimes it's ambiguous, then it's going to throw you an error. Okay, because you can easily think about such type combinations that you cannot decide whether it's A or B. When when it's ambiguous, you are going to see an error. But basically, for several operations, like for example, when you type a good function would be plus. When you type methods plus, you can see I have 100 without loading any packages. I have 189 methods for plus. It's going to behave differently depending on the type of arguments. Maybe depending whether it's a matrix, a vector, some other data structure, special array, and so on. It's going to behave differently each time. Yep. Can you define your own function, you ask? Yes, you can define. So usually when you define, for example, your own number type, then for your own number type, you will define your own addition function. Or, so you have always two options. You can use some kind of fallback mechanism to the default implementation. For sometimes it's tricky, but you can either use fallback or you can define your own function. And you will define your own function for two reasons. Why specific of your mathematics, specific of your domain area. And the second reason could be performance. Like, for example, we got out of a memory error for non-materialized matrix when if I had an efficient implementation, I would not need to throw an out of memory error. Yes, the same function can return different types depending on arguments. And this is a very good question. So suppose I have, let's say we have this function f from x, and I could write if x less than 0, then return, say, 1, else return 0.5. Okay, I could do this function, but this function is very bad. Why? Because the compiler, if the result of this function is assigned later to some variable, the compiler will never know if this variable is going to be in integer or float. And really, there is a warning mechanism. Sorry, called warn type f from 1. Okay, and it's showing you. And this is not so bad because it's either integer or float, just two types. It's called small union. And there are some tricks that the efficiency is not so much downgraded, but I get here a yellow warning. Okay, so this is a warning because I wrote a piece of code that sometimes is going to return an int and sometimes float, and compiler is tracking it. So what is important? You want to write a function which are type deterministic in the way that if you are providing a centered combination of types for arguments, from types of arguments, it's very important for performance. But then the efficiency of your compilation process is going to tumble, but you have tools for monitoring that, as you can see. You mean you have function that returns integer or string? Then you get and then you get an error. Okay, so you're asking about something. It will be a runtime error. Yes, you are asking about something like a equals 1 and 2, and you do something a from 1 equals f of from rand minus 0.5. So this is the case. Did I did it wrong? Why I should be getting error sometime. Oh yeah, okay. I had bad luck. Okay, so you get a runtime. So you get a runtime error in that case, like Julian has said. But here, this type is even. This case is even more ugly. No, it's still saying this is a yellow union, so I'm getting warning because sometimes you could get even like marked by red color, I think, for those. But basically, you get a warning. So this is not this is a not type stables code, and you should avoid. And of course, what you should do. So this is my data structure. I could define a instead of as a vector of union string and int. Okay, with values 1 to 3, string, not string. Okay, I could define a like this, and then it would be, of course, not prone to this error. But you need to be careful about code being type stable. Okay, so there are many more examples introduction, but they're left for you as reference. Of course, there will be always more materials that we can discuss, like, so you have background material. But after the break, we'll move on to data frames. Okay, and in case of data frames, we will be, in case of data frames, some other examples that I had planned that are later at this lecture that will be also illustrated. So don't worry about losing anything. And yes, so we have now like half an hour break. So let's start. So what's time? So what's time? 8 past 1. Half an hour break.